recording. I record all my online sessions, and I will make a copy of this to you tomorrow morning. And all it records is whatever is on my drawing tablet plus whatever we say to one another.
All right.
Okay. Now, as far as the source of the problems, do you have some stuff tonight that you want to work on specifically?
Yeah, I'll go get my backpack real quick. Give me like 10 seconds.
Okay.
All right.
The second question is, are these problems of a nature that you can verbalize? Or,
yeah.
Okay. Because if they were like graphs and stuff that you wanted me to look at, then you could always take a picture of those and email it to me. And at some point, you're going to come across a problem where it's just going to be simpler to do that. So we may want to go through that process at least once tonight. Have you take a picture of the material and send it to my email. Because once you do it once, it's always so much easier to do it the second time because it saves the email. You know, type in DA and my email address is going to pop up. But if you can verbalize them, let's go ahead and start.
All right. So my homework tonight was it's writing cubic functions with graphs that go through certain points. But I understand that pretty well. I thought that was super easy.
Okay.
Because you just plug the points in, like y equals a times x plus whatever, x minus whatever.
Right.
But I thought that was pretty easy. Everything we did today seemed mostly easy. And then we had to use the finite differences to determine the degree of the polynomial.
Okay. Do you have a specific problem? In other words, if you can give me a specific problem, I will write it out and then we'll solve it together.
So there's a graph. Can I just give you the points?
Yeah.
So -1, 0, 0, 5, 2, 0, and 5, 0.
Okay.
And then I just have to write the polynomial function, or the cubic function.
We have to write the polynomial function that fits this.
Yeah.
Okay. Well, there's a lot of zeros here. Every one of them has a zero, so there.
We just learned it, put it in like the y equals a times x minus k, x minus q, and x minus r, or something like that.
Uh-huh.
Oh, x minus p, q, and r.
Right. And you'll notice that what we're looking at is all x-intercepts. Well, one of them's a y-intercept. Okay, in other words, this one here is a y-intercept.
Yeah, don't you plug that in for a?
Right. Well, I don't know if you plug it in for a, but let's look at the x-intercepts. Okay, here's how we're going to solve this. In other words, we know that 3 of the factors have to be x plus 1, x minus 2, and x minus 5. Correct?
Yeah.
In other words, those are the 3 x-intercepts. Well, if we multiply all 3 of those together, we'll have a constant at the end of it. And that constant needs to be 5, because we can see that we have a y-intercept right there. So, first of all, let's multiply these 3 factors together. How do I do that?
Multiply 3 factors?
Uh-huh.
Don't you put x in as 0 and then just multiply 1 times -2 times -5?
I would no, multiply that times that. What do you get?
don't know, x squared plus 1 plus or minus x minus 2.
Okay, now multiply that by x minus 5, and what do you get?
X cubed minus x squared minus 3x plus 10.
I think it's plus 3x
Oh yeah, plus 3x.
plus 10. All right. So that's the polynomial we would get if we were just using the 3x-intercepts. Okay?
Mm-hmm.
But that would give us a y-intercept of 10. So therefore, A must be 1/2, right?
Yeah.
In other words, if I multiply this entire thing by 1/2, I'm going to get x cubed over 2 minus x squared over 2 plus 3x over 2 plus 5, and that will satisfy all 4 points. We know it's going to satisfy the 3 x-intercepts, and now it satisfies the y-intercept also. And notice that these functions are not the same. In other words, this is different than that. One is magnified. In other words, one might be this, and the other would be half of that.
Uh-huh.
It has the same zeros, but it's not the same looking function. In other words, if that goes through 5, well, the other function that we would be talking about would be this one here, which has the same 3 zeros, but it's not the same function, and it has a different y-intercept. So you solve for A by figuring out what the constant would be and what we know it to be. We know the y-intercept is 5, not 10. So we need to make A whatever it has to be for that to be 5.
So couldn't, like, we just originally put 5 there because the y-intercept was 5? Like, we knew that from the beginning?
Put 5 where?
For A?
Well, notice that's not what A ends up being. A ends up being 1/2. In other words, we didn't know what to make A. No, I don't think we can do what you're suggesting. In other words, you're suggesting make A 5 because of that?
Yeah.
No, because notice that when we multiply these 3 linear factors together, we get a constant at the end of that cubic. And that constant was 10. And we know that our function, the constant has to be 5, not 10. Therefore, A has to be 1/2. So, yeah, I don't know how you could plug it in directly for A. I think you have to multiply these 3 together in order to figure out what the constant would be.
Yeah.
And then figure out what A has to be in order to give us the point 0, 5. The only way you're going to have this function go through that point right there is if A is 1/2.
Mm-hmm.
All right. What else you got?
One of these. Okay, so it's one of the the finite differences.
Okay. Not quite sure what you mean there. Go ahead. I'll figure it out.
Well, there's like a table it has like two rows, X and Y, X on top, Y on the bottom, and then it's like if you were to plot some points.
Okay, give me
And
give me
there's a total of six. It goes 10, 20, 25, 30, 45, and 55 is the X.
10.
10, 20, 25, 30, 45, and 55.
Okay, what's the Y's?
4.5, 8.9, 13.8, 18.9, 29.9, and 37.7.
Okay. Stuff like this you might find easier to just take a quick snapshot and send it to my email.
Oh,
It
okay.
would almost be quicker for you. Although this is probably equally. Okay, and what's the question here?
It says the data in the table shows the average speed, y, in miles per hour, of the of the boat for several different engine speeds, x, and hundreds of revolutions per minute.
Okay.
Uh, Find the polynomial model for the data. Estimate the average speed for the boat when the engine speed is 2,800 RPM.
And this is in hundreds of revolutions per minute, right?
Yeah, and x is also the RPMs.
Right. So 2800 is between 25 and 30, correct? Am I understanding that correctly?
Yeah.
Okay. So it wants us to come up with the function.
So in class, we just on one of them, we made a little chart, just like the
This is
difference.
parts and points, graphs and points. What's the ultimate goal here? Is it to
Well,
graph?
in class, we just found out the difference between each one, and then
Ah, okay. I know what you're talking about now.
yeah,
So that's 10. That's 5. That's 5. That's 15. That's 10.
yeah,
And this is 4.4. This is 4.9. This is 5.1. Goes from 18.9 to 29.9.
yes,
It's 10. No, that's 11. Excuse me. And then this is 7.8. They want the polynomial function,
yes,
and then they want you from that polynomial function to predict what y will be when x is 28.
2,800,
Right, which is 28 on our table, right?
yeah.
Do we know whether this is a quadratic function or a cubic function or?
I don't. I'm guessing it's exponential since it goes up.
Yeah, it's definitely not linear.
Yeah,
In other words, this is going up 10, that's only going up 4.4, and then that goes up 5, and that goes up 4.9. 5 goes up 5.1. 15 goes up 11, okay, and then 10 goes up 7.8.
yeah.
So guess we could graph some points. I don't know that that's going to be real helpful. How did they teach you to do this?
We kind of just went down and just figured out, like, we'd go down another row and figure out the differences between those and then do it again.
Right, okay, so the difference between that is 0.5. Difference between that is 0.2. But the difference between these two, I mean, we have a huge jump up here. We go from 30, that was 30, correct?
Yeah.
We go from 30 to 45, and clearly we should go from 18.9, quite a big jump there. And then what?
I honestly don't know. I'll probably ask my teacher about that one tomorrow also.
Well, I'm sitting here trying to think of this, and they don't tell you if it's a cubic or a quadratic or.
Oh, no, it's not mentioning the problem. It's like oh, yeah, I don't know.
No, this is an analysis that I run into about once a year. And I'm not kidding. That's all I run into it. And I have literally 100 students in a year. And this is a different way of figuring out the relationship between stuff.
Yeah.
And in other words, you can tell if it's linear if the differences, I think, all have to be the same.
I think I just chose, like, the hardest one on the page.
You probably did, yeah.
Like, every other one I know how to do.
Oh,
that one.
all right. Well, that's what you're supposed to do, is you're just supposed to choose the hard ones. Let me think for a second. You think this is exponential, which means it has to fit this model, right?
Yeah. Well, I mean, I don't think it goes down.
Well, we can plot a few points and see what it looks like, what the graph looks like.
Like, I don't think it'd ever be negative.
No, it looks exponential. In other words, let's call that 4.5. Okay. And when it's 20, it's a little bit more, no, a little bit less than twice that. And then when it's 25, it's about there. It's actually looking almost linear at this point. And then when it's 30, goes up to 18.9. Let's see, that's 8.9. That's 13.8. 18.9 would be another 5, so that would be about right there. And 30 is right there. It's starting to look linear. 45, that would be way over here. And that's 29, going to be right way up there. If I connect those dots, now you're not doing linear regression, are you?
I don't think so.
Because this looks like a perfect thing to do a linear regression on. In other words, perhaps it's the way I've graphed it isn't quite right. You'll notice that my 25 needs to be a little closer to the 20 than it is. But when I plot these points, they appear to be linear. And yet, yeah, I'll bet this is a linear regression problem. It's not exactly linear, because for it to be exactly linear, these numbers would all have to be the same. In other words, well, that 10 is the same, pretty much. We're separating everything by 5 in the x's. And every time we move up by 5 in the x, we move up by almost half that amount in the y. In other words, we go from 10 to 20, and we go up by 4.4. When we go from 20 to 30, we go up by twice that much. So this looks very linear, but not exactly linear. In other words, we have some scatter. If I plot these dots, they might look more like that. Okay? And when you have data like this, first of all, you're trying to determine whether it's linear or whether it's quadratic. It could be a quadratic set of dots. And once you determine what this is a calculator problem.
Yeah, I think it is.
You put in this as list 1.
Yeah, I think that's what it is. That's what I forgot about.
And then you do a linear regression. And the calculator, what happens is, let me give you what's going on here. If I put a bunch of data points like that, okay, that appears to be a linear relationship. In other words, if I can fit the best straight line through that, that's a better fit than if I try to put a parabola through that.
Yeah.
Okay? But sometimes you have points. What if my points were like this? In other words, if I had a data point like that, data point like that, data point like that, now that doesn't look linear anymore.
Yeah.
That looks parabolic, which is quadratic. So what happens is that based on a set of data points, you can get both linear regression and quadratic regression or cubic regression or square root regression. In other words, let's say that I ask my calculator to do a linear regression of these points. It's going to come up with something like that. Okay? In other words, it's going to try to fit those points to a straight line. But if I ask my calculator to do a quadratic regression, it's going to put something more like that in there. In other words, it's going to make it fit a parabola. And it appears to be a quadratic regression, not a linear regression. The thing is that with any set of data points, you can fit it to whatever choices your calculator gives you. What kind of calculator do you have, Michael?
The TI Inspire.
Okay.
It's the graphic calculator. I just forgot that I had to do this. I know how to do it.
Okay, cool. And what you're going to end up with in the previous problem, in other words, this certainly appears to be linear.
Yeah.
So you're going to end up with the equation of that line. Well, equations of the line look like this. Okay? So what your calculator gives you is M and B.
Yeah.
In other words, it might spit out, if you input these two lists into your calculator and request that it do a linear regression, it might tell you that M is 1.2 and B is 0.5. Okay? So I would come up with the equation of the line is 1.2x plus 0.5 And then when it says make a prediction based on 2800 RPMs, plug that in for X, and the answer is whatever Y is. You understand?
Yeah. Yeah, I know.
But
I just forgot I had to put
when
it into
you
my.
do a linear regression on a calculator, and that's the only place to do it. I can't even do it manually. Okay? But you can do it on a calculator. You can do it on the Inspire. You can do it on the TI-84. You can even do it online and at Wolfram Alpha. But
Yeah.
if you request a linear regression, it's going to give you M and B. It's also going to give you a number called R. R is a measurement of how good the dots fit this straight line. If I do a linear regression and I have dots that look like this, and I ask the calculator to put a line through those, the best one it can do, it's got a pretty good line, right?
Yeah.
That's an R of 1. If I ask the calculator, if I give it a bunch of data points that look like this, well, it can still draw a straight line through that. That's going to be its best effort. But that's going to have an R of maybe 0.7. So R values go from 0 to 1, excuse me. If I had a bunch of data points that were just completely random, and I said do a linear regression of that, well, it's going to be able to do a linear regression. It's going to fit some straight line through that, but it'll have a very low R. It might have an R of 0.1, meaning that those points are not very close to that line. There's a lot of distance here. You know, that distance is a lot of distance. Whereas when I had all my dots lined up in a straight line, there was virtually no distance between any of the dots and the straight line. And that's what R measures, is the correlation of the data to the regression that you've requested. In other words, if I gave it all these data points here, gosh, I'm not even sure that looks like a straight line to me. I might not request a linear regression here. Maybe I'll request a quadratic regression. Maybe that fits those points a little bit better than a straight line. I don't honestly know. I would almost have to put them in a list in a calculator to find out.
Uh-huh.
Okay, but there's various regressions you can do. And the whole point of doing a regression is find out what is the best model equation that fits that data. Is it linear? Is it quadratic? Is it cubic? You know what I'm saying?
Yeah.
And each one will give you an R. And basically the R that is the highest, that's the best regression to use. Whichever one gives you a highest correlation coefficient, which is what R is. All right. You got anything else, last things that you need to ask about, or are you good to go?
That was all we worked on today.
Okay. All right. Well, you've had a online experience and in person now, and you can take your choice.
All right, cool. Thank you. Thank you, sir.
You're welcome.
And my mom wanted to ask about the payment way for this because she couldn't
Here's
find
the
it.
easiest thing to do is write down this web address, digital, www.digitalmathtutor.com. Here, let me just take you there real quickly since I have it. Okay, all she needs to do is to scroll down to where it says buy now. If she clicks on that buy now, in other words, say she wanted to pay for tonight's session. Put in $16 right there where it says item price, and then whatever her password for PayPal is. That's the way she wants to pay, using PayPal, right?
Yeah, probably.
This is the easiest way to do it. In fact, this is a lot easier than writing a check and mailing it to me, because the only thing she needs to put in is the amount and her PayPal password. Now, this information over here, obviously, I don't get. PayPal, this is a separate window that PayPal opens that allows her to put in her PayPal password, and that's all she does, and that makes the payment of whatever amount she's put in there. You know, if she wants to pay every time, that's fine. If she wants to pay every couple sessions and pay 32 instead of 16, that's fine also. That's completely up to her. Although this is so easy to do that, you know, it's only going to take her like 10 seconds to do this.
Yeah.
But the only thing she really needs to remember is digitalmathtutor.com. And she doesn't need to go to any page other than to scroll down to the buy now. And if you click over here on book now, you can schedule sessions. In other words, you probably used algebra to calculustutor.com, right?
Uh-huh.
When you scheduled your session, or if your mom scheduled it. And that's fine. You're welcome to use that also. It's just not quite as smooth as Digital Math Tutor is for paying. For paying, nothing is quicker or more easy than Digital Math Tutor. The other website that I use, you have to send a payment to my email address, which is a little bit more difficult. So this is the way I would recommend her doing it if she wants to.
So she doesn't have to pay every time?
No, if she wants to wait every couple times, that's fine. Or I'll send her an invoice every now and then. I keep pretty good invoices as long as I have her email address or yours. And let's see, do you have her email address?
Yeah.
Why don't you give it to me real quick?
All right. P. Koster, Koster,
Okay.
at Moran, MORAN, ANDCO.com.
Okay. Yeah, I usually send out invoices when they get up, you know, 50 or 60 bucks or something. Or she's welcome to pay every time, or however often she wants. I don't really much care. But I'm just telling that the easiest way for her to do all this is going to be through Digital Math Tutor.
All right.
Okay? If she wants to send me a check, that's fine also. I have no problem with that. But whatever she wants to do. Okay?
All right.
All right, Michael. I will talk to you next time. Have a good week.
Thank you. You too.
You're welcome. Bye-bye.